Good morning. Happy Friday. You all there?
Yeah.
Okay. Got a nice problem for you to try. Go ahead and get started on that. We have some challenges today. I'm teaching something that there's a lot of stuff in here that I haven't seen before. So I previewed it a little bit so we can make sense of it together today. That's kind of fun. I know sometimes we prefer somebody who can just tell us, how to do something. But there's something to say about true exploration and letting yourself reach some sort of frustration point and persisting through that so that you can actually learn it. Sometimes those experiences stick with us more poignantly. I wrestled with this for a little bit, and then once you understand, then it actually became quite simple. So you have to put on your science hats now and your logic hats and really think about what's happening in this problem.
I wish I had a hat for every problem. That'd be useful.
Yeah, I know. You use calculus to do these problems in calculus where you're filling up a container at one rate, but you're draining it at another rate. So you will, and they'll ask you questions like, how long is it going to take for the container to empty? And the containers can be differently shaped. So for a swimming pool, so we're on time here. So here we go. For a swimming pool with a rectangular base, Torricelli's law implies that the height h of water in the pool after a certain amount of seconds, t seconds, after it begins draining, is given by, so h is going to be a certain height at a given time, so it's going to change over time. And that's going to be equal to, so you're going to have this quantity squared. The quantity is the square root of h naught. That h subtext 0 is called h naught. And that is used, that naught symbol is used for an initial condition. That's where the height starts when the pool is completely filled. Okay, so you have to be careful with h naught and h and not mixing them up. Okay, so it's important. They are two different ideas. H varies. H naught is a constant. Okay, H naught is the starting position, which doesn't change. It's like an intercept. Okay, so they are two different things, and yet the idea of what they are.
Root 0 is 0.
If they're both at 0, but the pool doesn't start at 0. It starts full.
I know.
Yeah. So
something else.
H and H naught are equal to each other at the start of the problem. Okay, and then you get all these other things. So you have D is the diameter of the drain. Length and width are the dimensions of the pool. And you might be thinking, well, where's the height of the pool? Well, that's what's occurring in the problem. The height of the pool is being considered to be changing.
It's not.
The length and the width of the pool are not changing. All right, it's the height of the water that's going to go down. That level's going to go down over time. T is time, and you're going to have pi in there because the drain is circular. All right, and then you have some other values. So we're not going to explain all these values. I wouldn't be able to. Of course, we could put up a video to prove Torricelli's law and go through all of that, but we don't have time for that. So what we're going to do is we're going to assume that Torricelli's law is correct for this drainage problem. Now, it says all measurements are in inches. So in terms of L, W, D, and H naught, when they say that, what that tells you, you got to get used to this, is that your answer better have those variables or those letters, okay, in them. All right, they must have all of those in them. All right, and then it says, what is the time? That means it needs to be solved for time. So in the end, it needs to say T equals, and then on the other side, you better see an L, a W, a D, and an H naught, but not an H. H naught, but not an H. How do you like that? All right, so you have to somehow get H out of there, and what's left needs to be L, W, D, and H naught with any other constants are okay. If you have constants in there, that's fine. All right, like the square root of 3 could still be there, possibly. Pi is probably still going to be there. Okay, so those constants will remain. But your answer should be written in, and it should have L, W, D, and H naught on one side and T on the other of the equation. All right. Give me 1 second, everybody. You want the charger? No. There you go. All right. Now, all you have to do is realize one thing. Once you realize that one thing, then it's just some algebraic manipulation.
It's a binomial. It's a binomial squared, which means it's going to make a trinomial.
Okay. Is that going to help you solve the problem?
Yeah, if you know how to solve it by squaring it, you can get rid of this giant square on both sides.
Okay. Go for it. I'd like to hear your comments. Whoever has an idea, you can share it with us. Something that you're realizing. Any realization you come to, share. Maybe that would help everybody. Nobody's realizing anything?
Well, H has to be 0.
Why would H have to be 0?
Because we're looking for the time at which it's completely drained.
Yeah, and so what is the time required to drain the pool? When they say drain the pool, they mean completely, not just drain it partially. So what would a drain pool mean? It would mean the height.
0. The water level is 0.
That was it. That was the key realization, I believe, to help you do this problem. In the beginning, I was saying, I was doing H, I made H naught. I said, oh, they're both full because I looked at completely filled. So I made, oh, H is going to be the same as H naught when they're completely filled. Problem with that is this all goes to 0 then, right? Oh, I left out a T, didn't I?
One algebraic technicality. Why is it okay to divide when you have to divide by a certain number? You have to do it on both sides. But when you do square root, you divide by one number on one side and a different number on the other.
I don't know what you're talking about. I haven't done that yet. Okay, so wait, everybody, I want you to see, this is a multiplication of time. So all of this here comes out to some number. So this is all just a jumble of mess, but it's really just a value times the time.
Can you turn off the screen share?
So when, oh yeah, I could switch the screen, yeah. Thank you. Okay, so this here, this jumble here, times T, if T is 0, all of this is gone. What does that leave you? It leaves you the square root of H naught squared. And when you square the square root, it just becomes H naught is equal to H. So that means the height of your pool at 0 time is the initial height of the pool.
Really? I did not know that.
I know, but I want people to understand what this is saying. Okay, so now what's going to happen as time ticks, this value then is going to subtract off of your initial height, and then your that will lower your height until your height gets to 0 and your pool is drained. Okay? So over here, what I'm going to do is I'm going to actually separate this into two of the same thing. And so what I want to do is I want to think of this as now in intercept form. If this is an intercept form, then you can pull the root out of this. All right, and that would be when for what value of t would make this 0. All right, so what I would want to, since these are both the same, I don't need to do it for both. I just need to examine one of these groups, because whatever's true to make this group into a 0, to make it 0, then it's true of the other one. So
you can square root both sides.
Hold on, I don't need to do that. I don't need to do that.
It just eliminates one group and then you don't have to write it all.
I eliminated the group. I'm doing it to show students what's going on.
Oh, okay.
Okay. I want them to see two side by side so they know that if one of them is 0, then it makes it 0. Yes, you can take the square root of both sides. Okay, all right, so now if one of these groups needs to be equal to 0, then you have that equation, just you need to make this equal to 0.
The easiest way to do that is
you add this clump to both sides to move it over. So you get this. Okay? And then what you're going to do is multiply by the reciprocal, and you'll be all set. So t is equal to, I know there's a little bit of glare when we get to this part. I wonder if I do that. No, it's the glare is from the window, not necessarily from the light. Okay. All right. So if I have t here, then I'm going to have all of this here. I'm going to flip it over. I'm going to get LW root h naught. I'm multiplying it to that. And then this becomes the denominator. And you could say, well, let's rationalize the denominator. But look, pi is irrational. That's kind of weird. You can't rationalize the denominator when the denominator is pi, can you? You can't get rid of the pi by multiplying by pi and getting pi squared. Doesn't get rid of the square root, because you don't get to pi from a square root. That's not how you, so pi is worse than irrational. It's transcendental. So you're not going to be able to get rid of that there. All right. So here you have the square root of 3. You could say, well, let's rationalize that and multiply by root 3 over root 3. But for our purposes, this is good. This is what they're looking for. All right. So that if you had this formula, you could plug in for this swimming pool, you can plug in the length and width of the pool, the initial height of the pool, the water level, the diameter of the drain, and then you just plug it and it'll tell you how much time it takes to drain the pool. And that's it. Questions about that problem? All right. So the key to that problem was realizing that the h had to go to 0.
Oh wait, Mr. Rosenthal, how did you used to have rad h naught minus 2 pi d twice? How did you get rid of one of them?
Where?
From the second step to the third step.
Because all you need is one of these groups to be equal to 0. They're both the same group.
Oh.
If one of them is 0,
divide by one group.
If one of them is 0, then 0 times the other group is going to be 0. So I just have to make sure that I can solve to make one of the groups 0. Solve what was, solve for t. If t happens to come out to this, then when you plug that in for t, what's going to happen is this will cancel all this out to a square root of h naught. So you get square root of h naught minus the square root of h naught.
Oh, okay.
Yeah. All right. All right. All right, so today, look at that. Perform operations with complex numbers. Look at that fractal there. That is, does anybody recognize what that is?
That's a
A
fractal.
snowflake.
That is a special function.
Oh.
We're gonna talk about that in an example, I think, next
So
week.
happy. Complex numbers.
Okay, here we go. So not all quadratic equations have real number solutions. All right, so before we get into this, I'm gonna break away for a second and we need to talk about this. Because what you know about this already, some of you already know what I is, but let me just talk about something first. Let me say this. If we have x squared is equal to -1, what's the problem with that?
You cannot get a real number when you square root of -1.
Okay, because you cannot square something. A positive times a positive is a positive, and a negative times a negative is a positive. So this is not something that can happen in reality. So, but in mathematics it can. But here's a problem that we're going to get. Let's say that if you take the square root of both sides, right? Now the square root of x squared is the absolute value of x, right?
Yes.
And so x could be plus or minus this, right?
Yeah.
That's not what you're going to see the way that they teach it. And there's going to be other problems too.
It could be positive I or negative I. What's negative I?
Now, how do I put this back to the way I had it? If I square both sides like that, there's two ways to look at it. So in the first case, if I square a square root, I get where I started from. And it doesn't matter whether this is plus or minus, because when you square it, it's the positive. So we don't have to worry about the plus or minus when we square it back. Okay? So you see that? Squaring a square root, you just get the contents inside. For instance, if I have the square root of 5 squared, okay, that just is 5. It cancels it out. On the other hand, if I write it out the long way, -1 times -1, we have a rule in algebra. The rule in algebra says if you have the square root of a times the square root of b, that is equal to the square root of a times b. We have that rule. We learned that rule. Okay? However, watch what happens when you do that. If this is the square root of -1 times -1, what does that give you? It gives you the square root of +1, which is 1. How could the same thing give you 2? 1 is not equal to -1. There's a problem. Okay, so either this rule is not true when it comes to imaginary numbers, or imaginary numbers, you can try to get away with it by saying, well, it's because those are not real numbers. So weird things start to happen. So I believe it was Euler, Leonard Euler, the mathematician, who came up with a solution for that. What do you think that the solution was? How do we do things in geometry? We define things in such a way as to get around those problems. So there's two definitions. If you say that the square root of, if you say, we can say there's this term called I, and we're going to define that term as the square root of -1. But you're going to also define this I squared as -1. Now what's going to happen? Whenever you see the square root of -1, you must replace it with an I. And if you replace it with an I, then what's going to happen? You're not going to have this -1 times -1 situation. You're going to get a this situation. And if you get a that situation, then that becomes I squared, which you then refer to the other definition. It seems like complete trickery to me. It seems unfair, but that's the way that that's the only explanation that I've been able to find on that. Even I went to Mr. Knaus and we didn't have a great explanation for this. So he said they like to define I as this, and that there's something lost when you take the square root. is what he was trying to say. When you take the square root of both sides, there's something lost when you do a square root in getting to this answer here, all right? So anyway, that doesn't make a lot of sense to me either. All right, so that's my explanation. That's what Euler's explanation was, is that you can define these this way, all right? And then once you define them this way, so how is that going to affect us though? How it's going to affect us is when we get these terms this lesson, you're going to replace it basically with an I. All right. So let's go on and see what they have for us. And you're going to get to see some application in electrical engineering for imaginary numbers, which is neat. If you're thinking, well, how is this used? If it's not used, why use it?
Imagine that.
I know. Okay, so if you look here, it says imaginary unit I. So to overcome, okay, so here we go. It says what I said there. Let's just read through it. For example, x squared is equal to -1 has no real number solutions because the square of any real number, x, is never a negative number. To overcome this problem, mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equals the square root of -1. And then you can see that I squared equals -1, but that also has to be defined, because if you square I, we just saw that there's a problem. You can get a contradiction. Squaring I can give you -1 or +1. So the imaginary unit I can be used to write the square root of any negative number. So let's look at these examples. See that square root of -3? You've gotten those results before in algebra when you were using the quadratic formula, and they asked you, how many solutions are there? 0, 1, or 2. Okay, how many roots are there? 0, 1, or 2. If you got no solutions or you got 0 roots, it's because you had a negative as the discriminant. Now, if you remember what the discriminant is, it's the b squared minus 4ac. It's the part underneath the square root in the quadratic formula. And when that came out to a negative, you stopped there and you said, there are no solutions. And we talked about it in this class that it's when the parabola never intercepts the x-axis. It turns away before it ever touches it. So because it never touches the x-axis, it makes sense that there would be no real numbers that it would ever touch. I mean, it's self-explanatory, okay? But now we can go a little bit further and start talking about that in the imaginary sense. So take a look at the example. When you get a negative inside of a square root, all you're going to do is split that. So if you have the square root of -3, what you're going to do is you're going to split that into 3 times -1, which you can then split into that, which you can then say, oh, we define this as I. And there you have it. Root 3i. Root 3 times I. And now all of a sudden you don't have a problem with your square root of 3. So think of it as factoring out an I. Whenever you have a negative, no problem. Factor out an I, and then it's positive. And if you think of it that way, it becomes very easy to operate, which is what this section is about, operate with complex numbers. By the way, we're going to learn that this is called a pure complex number. It does not have a real part to it. Okay?
So wait, if it doesn't have a real part to it, shouldn't it just be a pure imaginary number?
Pure imaginary, or yeah, you're right, pure imaginary.
This isn't complex.
Yeah, pure imaginary, you're right. Okay, and then look at this other case. When you have I root 3 squared, what happens when you square the I? Well, the I squared is -1, and then root 3 squared is just 3. So you get -1 times 3 is -3. Okay, so that's how that will work the other way. Any questions about what you're seeing there? No questions? All right. So I'm going to let you solve this problem then, and this should be fairly straightforward. This one right here. 2x squared plus 11 equals -37. Go ahead and solve that. Take a minute and we'll go over it in a minute. Okay, here we go. We'll go to my screen. Okay, so I have this, and maybe you subtract 11. 2x squared is equal to negative 48. You divide by 2, and you get x squared is equal to negative 24. And then you take the square root. Okay, you factor out an I. Right? Now, x squared, it should be plus or minus, right? It's the absolute value. All right, but then you factor out an I and you get this, but you still have to simplify your radical. So the square root of 24 is going to be 4 times 6. So it's going to be like that. So you're going to get 2 rad 6. So you'll just make this plus or minus 2 rad 6 I. Any questions about that?
Is it better to write the I before or after the problem? Because in the
I was
the
asking.
examples given in the textbook, they show it being put before, but you use it after. Which one should we do?
It's commutative, and later on when we start writing these in complex form, the I will come second. Now, I don't know why they put it first here. It should not matter. But when we write this as a complex number, that root 2 root 6 is going to be like a coefficient. We're going to write them in the future in this form as complex numbers, a plus bi. That's a complex number. So you'll see the coefficient of I is going to be written first. All right. So that's why I like to write it that way. Okay. All right. No questions, huh? That's straightforward to you? Great. There you see it. Okay. I think we're going to have another one for you to try. Okay. That's the same one. And maybe, oh, why does it do that? Okay. Let's see what it has for us here. All right. So complex number. So we already kind of jumped ahead and just mentioned that, but let's take a look here. Okay. Oh, here we go. All right. So a complex number written in standard form is that a plus bi that I was telling you about. You can see that there. All right. And where a and b are real numbers, of course, and the I is not, the number a is the real part of the complex number, and the number bi, right? It's like it's I, but it's scaled up some. B could be 1. Okay, but but bi, that term is the imaginary term. It's the imaginary part of the complex number. Now, what if b is 0? If b is 0, then you don't have any imaginary part. It gets eliminated from the problem. All right, you have 0 i's, right? That means you don't have any imaginary part. Okay, so a plus bi is considered an imaginary number. All right, now, what if a is 0? If a is 0, you don't have any real parts to the number. So they call that a pure imaginary number when you don't have an a there at all. All right, so if you just have bi, that's it. All right, so now look at that. Look at the table on the right and look at the right column. Examples of complex numbers or imaginary numbers are 2 plus 3i, 5 minus 5i, where 2 on the first one, 2 plus 3i, 2 is the real part, okay, and 3i is the imaginary part. That's an imaginary number. A complex number is an imaginary number. But if you look in the blue little box there, if you just have negative 4i or you just have 6i, that's just a pure imaginary number. There's no real part to it. the coefficient is a real number, but the whole thing, the whole term, there's no realness to it. It's just an imaginary scaled in a certain direction. Okay? All right. Let's see, sums and differences. So if you look at that, you add real to real. It's real simple. Or you subtract real from real. You add the imaginary part to another imaginary part. You do not mix them. Okay? You do not mix them. All right? So
obviously, this result is intuitive anyway. All you have to do is when you have plus bi plus di as you would in regular binomial addition, you just factor out the b plus d.
yeah, and that's the same as when you're adding like terms. You really treat it like a variable. Okay? All right, so you guys can try these out. Write the expression as a complex number in standard form. We want it to be a plus bi. We want the real part and we want the imaginary part. Okay, so go ahead and write those. Shouldn't take you very long. Should actually be fairly quick. Be careful, you have to distribute your minus. When there's a minus to a group, you have to distribute it to the group. Okay, another 10, 15 seconds here. All right, let's take a look. So in the first one, this is my real part and this is a real part. So you're going to add them and get 13. Okay, here I'm subtracting 1i plus 4i is plus 3i. It's really just as simple as that, and you're done. Okay? Any questions about the first case before I go to the second case? So this is complex addition. So now we're going to do complex subtraction. It's really not, I mean, there's not much to it. You will all be, I think, proficient in this. Okay, so you have that. So you are subtracting the 3 and you are adding the 6i. That's the one thing that students can mess up. So 7 minus 3 is 4. Negative 6 plus negative 6i plus 6i is gone. So your answer is just 4. So your answer is real. Questions about that one? Wow, you guys are quiet today. I guess this is an easy topic. Yes, somebody put it in there. Mitchell, the Mandelbrot set. Yeah, look up the Mandelbrot set. It's really interesting. It's a function in which when you plug something in, your answer then has to be re-plugged into your original. And you see what pattern comes out of that. And that's what that first picture I showed you that I said looked like a fractal.
Yeah, the Mandelbrot curve is like the Woody snowman.
Yeah, but that's how you got it. It's by plugging your answer back into your initial function. Okay, let's take a look at this. We have to subtract both of these. So you have 10 minus 6 is 4, minus 7i plus 4i. And then so you
minus 3i.
Minus 3i. And this is your final answer. Simple as that. Questions about that?
Hey, Mr. Rosenthal?
Does anybody need more practice with this? We can skip the guided practice for this if nobody needs it. If you need it, we can do more. But it really is.
Yes, please.
Wait, David, hold on. I need to see if people need more practice.
Actually, I'll after.
Wait, hold on, David. Wait, hold on. I need to hear if somebody says yes or not.
Yes,
Mr. Rosenthal, for number 2, could you write it as 4 plus 0i, since you're supposed to be writing it as like a plus bi?
The book doesn't do that. They did write that at first. They put 4 plus 0i. They did write that, but then they took one extra step and said equals 4. So I wouldn't mark it wrong either way. And next year with your Algebra 2 teacher, let that teacher tell you how they want you to write it, as long as you understand the concept. Okay, so somebody wanted to see more, so we're gonna do it. Here's the more right there. So you can try, let's look at number 7. (9 minus I plus -6 plus 7i. Okay, for those of you wanting to see more of these, I'd really like a question though. If you want to see more, I really want to know, what was it that seemed like you're not sure of what? I want to know, because I don't want to just do more just because some of you want to draw the lesson out more. I don't know. I don't know if that ever was true or if it was true or not. I just got the feeling during the year that there were some that just wanted to make sure we didn't finish so that you didn't have homework to do. You know, that kind of thing. We really don't want that at all. It really is, if that's the case. I'm not going to say that that's the case, but if that's the case, we really want to get that out of there, because that has nothing to do with the Science Academy and the way that we want to. It's the learning that matters, not the home. I know that there's a real component to that there is homework. It adds work to your schedule. Okay, but I'm giving you guys plenty of time to do it.
No, I was thinking earlier, most homework, you could render quite a bit of remedial homework obsolete if students were simply encouraged to continuously review the subject without the necessity for homework.
Yeah, it's just if you don't have
but you can't
structures, then people won't do certain things. Some people will not.
Yeah, that's the point. You can't do it right now because people are already after years of schooling, and certain habits have developed within most individuals, and now they're hardwired to have to receive a push towards the right direction. If that weren't the case, then most homework would be unnecessary because the students would take it upon themselves to review the material.
That would be ideal. It would be
yes.
Yeah, that would be great. Then it would save a lot
That's
of
what's called magic.
It would save tons of headache if we could just do that. But
so why don't we try it for teachers and students?
No. It's already been tried many times to remove those incentive structures. We're going to see a mass.
Not asking them to remove those incentive structures is too late for most students in the grades above 3rd or 4th grade. But the incoming students, those who are new to the concept of school entirely, all we have to do is make sure that never actually that method of thinking never actually reaches them.
Ah, I love that. That's such a
But
good
sir, you're forgetting the
Yeah,
fact
but what
that
about
humans
foreign
suck.
transfer students who come from somewhere else? So the removal of the reward system would make it worse for them.
Our
Which is pretty
foreign
bad.
transfer
Students never
our
knew about the
foreign
reward
students-
system because parents never told them about it.
Are foreign transfer students the majority of the students in the population? No, in that case, it's not something to consider. And
Well, it's not
all right,
fair
guys,
then
I'm going to put a stop. Okay, that's great. It's great conversation. You guys, that's a great conversation, but we're going to move forward now. Okay, does anybody need to see number 8? Now I feel like I pressured you to not say anything. If you need to see it, I want to know. But then I'm just asking you to follow up in good faith. Tell me why you wanted to see it, not to try to prove that you're trying to extend the lesson. It's just I want to know where you were confused so that I could help you. But just to have random problems, let's do another one for no reason, I don't want to do that. All right, so does anybody need to see number 8? Now I feel like I scared people away. Let's go back. I'd rather it be drawn out and people be able to ask when they don't know. Okay, so that looks like there's no difference in these. Does anybody have any questions about these? You can see they answered them for you there. Those are the ones we already did. Ah, okay. So this, somehow I didn't I really bumbled this one up. I did not get a picture of all the problem. So I'm going to have to write.
Ooh, the resistor, the inductor, and the capacitor.
Yeah, do you guys already know about these circuits?
Yeah. Well, most of
Who
us.
doesn't?
No, let's go over them again.
Yeah,
I
but
think
did,
all of us do.
but did you learn?
Yes, we,
No, I don't know about them. Let's do them
we
again.
did the
David, how
electrical
dare you
circuit.
Excuse
assume?
me,
Yes,
excuse
we
me,
did
hold on.
Interface.
Excuse
We
me,
did the electrical
Maybe
circuit
some
in
excuse
Makerspace.
pay
me,
attention,
excuse
huh?
me, excuse me. Please stop. Okay, thank you. Okay, did you cover this in an academic class?
Yes, Makerspace.
Yes, I am a bit cloudy on the inductor, but the
Notice
resistor
it's only-
capacitor I know perfectly
Okay,
well.
just a simple answer, yes or no. Did you guys cover these?
No.
Okay.
Yes, we
and-
did.
No,
Now,
only
for
like
those
3
that
people
did,
don't
no,
want
no,
you to
it
go.
was a yes or a no. Okay, now listen. If for those that did cover this, did you use imaginary numbers to talk about this?
No.
No, that's for sure.
Okay,
This is the electrical engineering, Jay.
so then what I'm going to do is I'm going to draw what I have in my book because I didn't capture that in the picture. So this is an alternating current source. Do you guys know the difference between direct current and alternating current?
Yes.
Yes, alternating current switches between polarity.
Okay, so the flow goes back and forth, right?
Yes.
Phrase it like Mr. Wilson.
With direct current, it just goes in one direction.
Yes.
Okay, so this is the drawing that we have. They have this. Okay. And then you get the twisty. And the twisty is called an inductor. Then this comes up and it comes across. And then you get a resistor, looks like this. Okay, and then you come across here, we come down, and now you get a capacitor. Now ask me what each of these are for. I couldn't tell you. Maybe one of you could tell us
What are these for?
Capacitor stores energy.
Okay,
The
For a
okay.
temporary period of time,
The
then
resistor
discharge it.
slows circuit. The resistor
Yeah,
slows electricity, and the inductor, I forget what it does.
The inductor
Yeah, I don't know
regulates
about the
circuit
inductor
and
either.
makes sure that it's a
The
regular
inductor
amount of current.
inducts things.
Let's do one at a
Yeah.
time. So Zig, what were you saying about the inductor?
Deduct
The
jumps over
inductor
defense.
makes it so that there's a regular amount of current. It's not like haywire, because when it goes through, it
So it moderates the current.
yeah, it moderates the current.
Okay,
It's not the extremes.
and then tell me again, what does the resistor do?
Lowers the overall current.
It lowers the overall current. And then what does the capacitor do?
Temporarily stores the current.
Ah, okay.
It stores it up and then releases it
Then
in 1
discharge it.
volt.
And this is the source.
Yeah.
Okay, so the power's coming from here. It goes around the circuit. Okay, now I'm going to read this to you as you look at this.
Okay.
It says circuit components such as resistors up here, okay, inductors here, all right, and capacitors here all do something. They all oppose the flow of current. What does it mean to oppose?
Slow it.
All
Or stop
those
it.
who oppose me will be destroyed. That's what M. Bison in
All opposed?
Bison in Street Fighter 2 used to always say that when he.
Oh, I love Street Fighter.
Yeah. All those that oppose me will be destroyed. So opposing means to go against. So these things.
All in favor? All opposed?
Oh, all right. Okay. Yes. And all of these are going to go against the current as the current is coming through. Now the current is going to switch, but it's going to go through the circuit. Okay. And then as it goes through an inductor, resistor, or capacitor, there's going to be resistance or reactance. So this opposition is called resistance for resistors. So for the resistors, there's going to be some sort of resistance
is futile.
measured in, what's this symbol?
Ohms.
Those are ohms. Okay, so this is
Ohm.
ohms. All right, so, okay, so then you have that resistance. And then for inductors and capacitors, it's called not resistance, it's called reactance. It's reacting. Okay, but all of that, a circuit's total opposition, if you add them all up, is called its impedance. So that's all the resistance and reactance you're going to get as it travels through the circuit. Impedance. Okay, so there's going to be some total impedance to the circuit. Okay, All of these quantities are measured in ohms. All of them are in ohms. All right, even though they're different components. All right, so let's go back to the table that we have. Look at the impedance that it causes. A resistor is going to be expressed as a real component, but inductors are going to be imaginary. Okay, so and you're gonna use those variables: R for resistor, L for the inductor. That's the reactance of it, and the reactance from the capacitor will be C. All right. But the impedance that it lends to the total impedance of the current, it's going to be Li, and it's going to be negative Ci. All right, so you got to remember that. Keep that in mind, okay, as we go through. We'll write those down. So you have
I
Li
believe that
and
I believe it.
negative Ci. Okay. Go ahead. Question.
Oh no, I was just going to say that I believe that in the fields of electrical engineering, they tend to use a J instead of an I because I is used to represent circuit in some instances.
Okay, well, thank you for that. All right, so the table that we saw showed the relationship between a component's resistance or reactance and its contribution to impedance. So you can see there underneath that the lower row is the contribution to the overall impedance in the circuit. So a series circuit is also shown on what I did on the board with the resistance or reactance of each component label. So I'm going to show you go back to my circuit. So take a look at that. Now you can see, oh, as the current comes through, 3 ohms of reactance here, 5 ohms of resistance here, and 4 ohms of reactance here, and then it comes back to the source. Okay? The impedance for a series circuit is the sum of the impedances for the individual components. What I want you to do is, after I've told you this here, okay, so see these? You cannot just use 3 plus 5 plus 4. That's not how it works. You must use them this way, okay? So now, and it won't be difficult to do, find the impedance of this circuit. Go. It won't take you very long. Okay, probably done already. Okay, so if you want to start with the resistor, you're going to get 5 ohms from that. All right. From the inductor, that's going to be Li. It's going to be plus 3I. All right. And then
Minus 4i.
Right, from the capacitor, that's a 4.
5 minus 4i.
But that's a negative. So you have to do negative 4I. Okay. And so then you just get 5 minus I ohms of total impedance.
Was that really that hard?
No.
Was that really supposed to take this long?
Yes, because I wanted the application to be important. The math
Oh.
itself was simple. The math itself is simple, but the application of it is, I wanted you to see that there's a real application in electrical engineering. Okay. All right, so then so if you're working with that, with electrical circuits, then you would see a certain amount of ohms written as a complex number of ohms. You can. Okay. Let's see what we have next. Okay, there's that. I saw that term pop up there. You see that bad word right in the middle of the screen there?
Foil.
Foil. Yeah.
No, not foil.
So to multiply 2 complex numbers, use the distributive property. Let's just stop there. Use the distributive property. That's all you needed to say. You don't need to say FOIL. Just use the distributive property as you do when you're multiplying real numbers. All right? So, oops. There we go. Go ahead and do A and B, please. I don't know how this came out so choppy. Lesson. not happy with the result. I will do better next time. Okay, for I, assuming the math here is really straightforward. It's in, I feel like when you get to your homework though, you got to be really, I bet you those problems, some of the word problems are going to be tricky. So hopefully if you paid attention, you're going to get more of those circuit problems that are more difficult than the one we did. So hopefully those are fun to figure out and not a burden to you. Okay, I think we should be done. And let's take a look. 4i times this quantity, you will distribute and you'll get negative 24i plus 4i squared. And you can't leave the I squared there. We know that I squared is defined as negative 1. So this is just 4 times negative 1.
Negative 4.
Right, so this is negative 4, and we want to write it in standard form, so this becomes the real part. So negative 4, I'm going to move over here, minus 24.
So 4 plus 24.
Negative 4 minus 24i is how I would write it.
So 4.
This is standard form. Any questions?
So 4 plus 24i times I squared.
Okay. But no, but this is how you write it. This is standard.
Okay.
Okay. Any questions about this? I'm going to let you, I'll give you a second here to think about any questions you have.
Didn't the people just write, couldn't you have written instead of negative 24i, 24i cubed?
What is I cubed? I cubed
It's negative I.
I cubed is I times I, or I squared times
So
I.
negative I.
If I squared is negative 1, then it's just negative 1 times I, or negative I. Okay? So I cubed is negative I.
That's weird. But okay.
I to the 4th would be 1, right?
1, yeah.
Everybody, let's look at that. What's I to the 4th? It's I squared times I squared, which is negative 1 times negative 1 is 1. Okay? I squared gave me negative 1.
And I to the 5th is just I.
So what you're looking at here is if I want a function to oscillate between 1 and negative 1, if I want to oscillate something between positive 1 and negative 1 and have it keep going back, look at what you can do.
Just keep increasing the exponent of I.
You just keep multiplying, yeah, you just keep, but multiplying by I squared is multiplying by negative 1, which makes sense. It would bounce it down. But what if you wanted to do, instead of going all the way, you needed some halfway?
Just keep multiplying by I over and over again.
That would give you some kind of practical use.
Y equals I to the power of x.
Hold on. It would give you some middle zone. From going from negative 1 to 1, you would get some middle zone. Remember we talked about a reflection in geometry? We could see a reflection as if I had an arrow pointing this way and I reflect it and over some axis this way, we could think about it as a rotation through what's called a null space, a space that doesn't exist to anything that belongs on that flat plane, like flatland, right? There's to the arrow, this space out here doesn't exist. So we call that the null space, right? Well, we could think of maybe a multiplication of I as halfway to your destination during that rotation. I don't know, can you guys see that hold on. Can you see that my marker is pointing towards you?
Yeah.
I can.
Okay, so you can see that according to these flatland creatures here, these arrows, we talk about it as a reflection, but we could think about it as a rotation through this space that doesn't exist with respect to the plane of it, right? And so I can go halfway, and that would be like multiplying by I. It allows me to do a 90-degree rotation, actually. And as a matter of fact, Mr. Knaus is going to teach you how to perform rotations in program using imaginary numbers so that you can get this rotation here. and then multiply by an I again, and you've created the negative of where you've started.
Desmos seems to regularize.
Hold on, let me finish my thought. You guys, put it in the chat. Put it in the chat. Don't interrupt what I'm saying. So here times I again, and you actually get a rotation through the null space. Okay?
Mhm.
All right, so it just seems more interesting as we investigate this further. Okay, so let's go now to,
Could you represent the rotation as simply a two-dimensional rotation if you just had the number line representing all real numbers and the line perpendicular to it representing all imaginary numbers?
yes, and that's at the end of this lesson, you're gonna see that.
Desmos recognized I.
It's gonna be the imaginary plane. Okay, let's
Mr.
we're running short on time. David, what is your comment? David, go ahead.
And I plugged y to the equals x to the power I to the power of x into Desmos, and it I mean, y equals I. It did a y equals x pattern, but then when I added to the power of x, it wanted a slider for I, so I don't think it recognizes it.
You can message Mr. Knaus about that or look it up.
Okay.
Okay, here we go, because he's the Desmos master. Okay, so here we go. We have 9 times -4 is -36. You have 63i positive. Here you have positive 8i. And here you have negative 14i squared. Okay, so your imaginaries come out here, but this, you know, is going to turn this to be, it's just going to be a -1. So that makes that plus 14. So now I can add 14 to that and get -22. Here I add these together to get plus 71i. I'll take questions if you have any. I wonder, are there any of you out there that don't know how I got this -22 there? I had to add 14. Why would I add 14? It says subtract 14i squared. Well, I squared is -1 times 14, -14. So positive 14 added to the -36 gives me that. Questions about that? All right.
So I squared is -1.
It is. It's defined as -1. Okay, now on to conjugates. It is Friday, and I don't want to try to rush through this, so you are dismissed. We will continue this when we come back on Monday.
Thank you, Mr. Rosenthal.
Thank you, Mr. Rosenthal.
You betcha.
So, Mr. Rosenthal, I think you're right about conjugation being distributive. Well, I think it
Thank you.
is distributive, but I think you're right about how to prove it.
Oh, how to do what?
How to prove it.
Oh, what did I say about it? Remind me, please.
Oh, so I was I asked you to. So I said if we take two complex numbers a plus bi and x plus yi,
Uh-huh.
and I was asking that in order to prove the conjugation is distributive, how would you take the conjugate of a trinomial yeah?
Uh-huh.
Because if you multiply these together, you would end up with a trinomial.
You get ax plus ayi plus bxi plus, it would actually be minus by.
And then if you factor out ay plus bx, the I gets factored out. And I think that if you said if you reverse that, then it becomes a conjugate.
And then here, this would be, you would put the real part together. I put these together here.
Oh, I see. And then all you'd have to do is take the conjugate of the imaginary term here.
Okay, a plus bi, a minus bi. And do what?
No. See, the proof was that what they're asking you to prove was that if you multiply two complex numbers in that form together and then take their conjugate, it's the same as taking the conjugates and multiplying those together.
Okay, so then the conjugate of this term would be minus this.
Oh.
Right? There's the conjugate of the one above. And so now you're saying if I multiply these and I multiply their conjugates, I should get this. Let's see. A minus bi times
X minus yi.
Okay. So then I get ax. I get minus
Minus
yi
AYI minus
my-
BXI
bxi.
plus, oh, no, minus BY.
Yeah, it's going to be minus by. Okay.
-1 times -1 times -1.
Hold on, I'm going to put those together. I'm going to get ax minus by. Okay. These are both minus, so I'll pull out the minus, and I'll pull out the ay plus bx pi. And it does match this exactly.
It is the same. All right. Thank you, Mr. Osta. Have a good day.
Okay,
See you
Mr.
tomorrow.
Interesting.
I
So
mean,
to show that the product of two conjugates is the same as multiplying them and then taking the conjugate. That's a good property. I like that.
thank you, Mr. Osta. Have a good day. See you next week.
You
Right,
bet.
Okay,
thank you,
Mr.
Mr.
Osto?
Osto.
Bye, guys.
Have a good weekend.
You
Hey, Mr.
too.
Vento,
Yes.
would you happen to have Miss Ebert's email or something?
Miss E.
Because on textbook return on locker clean out, I need to get into my locker, but I forgot the combo.
Oh, you need to contact Miss Huff.
Okay.
Okay.
Do you know her email? Because I don't.
jhuff@lausd.net, I believe.
Okay. Okay. Thank you, Mr. Vento. Have a good.
Okay. Anybody have any questions for office hours? Okay. Have a great weekend, everybody.